When it comes to the strengths of ionic and covalent bonds, this is something that scientists always wonder too. And there's a lot of energy transfer in these different things. Now, strength can mean stronger, which can be good, but strength, when stronger, also usually means less reactive. So sometimes a weaker bond is preferred because it's more flexible, all right? So covalent bonds are usually used in life. DNA, caffeine, all sugars, all those kind of things. Those are all covalent bonds. They're more flexible. They're not as strong as ionic bonds, but they are more flexible, and that's really important for life. So bond order and bond energies are used sometimes to tell like how strong bonds are, stuff like that. Ionic bond strength, if you want to ever calculate it through crystal lattice stuff, you use what's called a Born-Haber cycle calculation. And it's kind of a cool thing to do. It's nothing we're going to study in Chem 222, but if you want to look in the textbook, it is kind of fascinating. At the end of the day, you just need to know that ionic bonds are stronger than covalent bonds. We're going to focus more on the strengths of covalent bonds, but Born-Haber cycles are cool things that are done in inorganic chemistry circles sometimes to figure out the strengths of things. But again, we're going to focus more on covalent bonds in this quarter. Now, in Chemistry 221, we very briefly looked in Chapter 5 at this slide right here. And I talked about at the time a comparison that you can make between molecular orbital theory and Lewis structures. And we talked about at that time how like the triple bond there in acrylonitrile, that had a bond order of 3, while the bond order of 2 represents a double bond. And most of these bonds were single bonds, bond order 1, all right? And as a general rule of thumb, as bond order goes up, so as you go from a single bond to a double bond and a double bond to a triple bond, as bond order goes up, your bond length goes down, all right? So a triple bond is actually a lot smaller than a double bond, and double bonds are usually a lot smaller than single bonds, which is kind of cool. This was what we saw in molecular orbital theory too, but not quite the same way. So when we talk about bond order, all right, just remember this. A double bond is 2 bonds, and that's actually smaller than a single bond, but a triple bond, bond order 3, would be even smaller than a double bond. This is a question we saw last quarter too. It says, what's the carbon-oxygen bond order in formaldehyde, this structure right there? So we look for the number of bonds between the carbon and the oxygen. The carbon and the oxygen have 2 bonds between them. That's a double bond, so that would be a bond order of 2, all right? The carbon-hydrogen bonds, each of them have a single bond between them. Those would both be a bond order of 1. So bond order of 2 is what you'd see for carbon-oxygen. Bond order of 1, even though it doesn't ask for it, would be the carbon-hydrogen bonds. We talked about how as bond order goes up, the bond length goes down. So bond order 2, a bigger bond order, is shorter than bond order 1. Likewise, a bond order 3 is even smaller than a bond order 2. So bond order goes up, bond length goes down. But another thing you can do is talk about bond energy. And bond energy is proportional to bond order. So what that means is that if a bond order 1 is, say, 300 kilojoules, a bond order 2, bigger bond order, would be have even more energy, maybe 600 kilojoules. And a bond order 3 would be an even bigger number of energy yet. So repeat after me here. Bond order is proportional to bond energy. Bond order goes up, bond energy goes up, etc. But bond order is inversely proportional to bond length. So bond order goes up, bond length goes down. And that's going to be an important thing to realize. So in that picture up there of formaldehyde, once again, we have carbon-oxygen bonds and carbon-hydrogen bonds. So notice that the carbon-oxygen double bond, 745 kilojoules. That's the energy required to break that bond apart. And that's quite a bit bigger than the carbon-hydrogen single bond, That's only 414 kilojoules to break up. So bond order goes from 1 to 2 when you go from CH to CO, and the bond energy goes up quite a bit too. Now, I'd like to do the bond length thing here, but you can't compare carbon and oxygen to carbon and hydrogen. So bear with me here a little bit. But those picometers, which is what that unit is, those picometers are a unit of length, and people can measure this with x-rays and stuff like that. Down here in the lower right, I have some units that are used a lot in this section. An angstrom, which is an A with a circle on it, is 10 to the minus 10 meters. And sometimes in lengths, this is used, they'll either use angstroms or picometers, which is what they're showing up there. A picometer is 10 to the minus 12 meters. And remember that bond energies are often in kilojoules, where a kilojoule is 1,000 joules, stuff like that. Here are 3 carbon-oxygen bonds. The first one in the upper left is methanol, which has a CO single bond. The second one is carbon dioxide, which has a CO double bond. And carbon monoxide, the third one there, is a CO triple bond. Now, those values in red are angstroms, 1.410 angstroms, 1.317 angstroms, 1.194 angstroms. Here's what I want you to dig. Carbon-oxygen bond order goes from 1 to 2 to 3. It's getting bigger as you go down to the right, but also as you go down to the right, the carbon-oxygen bond length goes down. You go from 1.4 to 1.317 to 1.194. So bond order is going up, bond length is going down. And this is what you see. You have to compare the same kinds of bonds, so just carbons and oxygen, stuff like that. But it's pretty cool. And this is what people see when it comes to covalent bonds, bond length, bond strength, stuff like that. Pretty cool. This shows bond length as related to different kinds of atoms. Now, all of these are bond order of 1. Hydrogen fluoride, hydrogen chloride, hydrogen iodide. But notice how the bond length is getting bigger. Now, what's happening here is that if you remember from Chemistry 221, sizes of atoms get bigger as you go left and down. And fluorine is on the periodic table, chlorine, and chlorine is on top of iodine on the periodic table. So the atom sizes are getting bigger. Fluorine is smaller, chlorine's in the middle, iodine is the biggest one of all. And notice how the size of the bond length is getting bigger as well. So bond length definitely depends on the types of atoms, and that's why earlier I couldn't really do the bond order, bond length thing because we had carbon, oxygen, and carbon, hydrogen. But here I can show you why. Single bond order, they're all bond order 1s, but the atoms themselves are getting bigger, and that's why the bond length increases as well. So remember, sizes get bigger as you go left and down. Down is more dramatic usually than left, but that does happen both ways. Kind of a cool thing to remember. There's always going to be some optimum distance between the 2 atoms in a bond, all right? If it's too close, you start to have lots of repulsion. Too far away, there's not enough glue to happen. So what scientists have done is they figure out average bond enthalpies per bond. And these aren't perfect or anything because a CH in, say, methane might be different than a CH in methanol or something like that. But overall, these work pretty good. And when you don't have anything else to measure outside of these, then they work amazingly well. So in the upper right-hand corner right there, we have a whole bunch of different bond enthalpies. And those are the energies required to break the bonds in half. So C and H there at the top is 413. That's kilojoules per mole. CC is 348 when it's a single bond, CN 293, etc., etc. So those are for single bonds. But notice especially here the CC single bond, and now compare that to the CC double and the CC triple. A CC single bond, 348 kilojoules per mole, is a lot less than a CC double bond, 614 kilojoules per mole. And the CC triple bond right below that, 839 kilojoules per mole. So we're seeing bond order go up, single bond, double bond to triple bond, and the bond energy goes up. We're going from 348 to 614 to 839 kilojoules. So the more bonds you have, the more energy you have to add to break them all. That's why bond order goes up, bond energy goes up. On the other hand, bond order goes up, bond length goes down. So in the lower right-hand corner, we have an oxygen-oxygen double bond and an oxygen-oxygen single bond in hydrogen peroxide. So notice that the bond order 2 has more energy to break than the bond order 1. However, the bond order 2 is a smaller bond. The bond order 1 is a bigger bond, 121 versus 148. So again, bond order goes up, bond energy goes up, but bond length goes down. You can use these kind of bond enthalpies to calculate delta H of a reaction. And for these kind of delta H calculations, you almost always need to draw some Lewis structures. So it might be a good idea to remind yourself how a Lewis structure can be drawn and stuff like that. In this example, it's not too bad. We want to form HCl from hydrogen and chlorine. And when you draw the Lewis structures out, HH is a single bond, chlorine is a single bond, and HCl is a single bond. So when you see a question like this and it asks you to find the delta H, it's always delta H of the reaction equals bonds broken minus bonds formed. And in these kind of reaction, that means the bonds of the reactants minus bonds of the products, the bonds that you form. And here are the three values of HH, ClCl, and HCl that we'll need here in a little bit.
Hydrogen and chlorine react to form hydrogen chloride. Because the total energy of the broken bonds is less than that of the bonds formed, the overall reaction is exothermic.
Using a table like the one I just showed, you want to do bonds broken minus bonds formed. So that means reactant bonds minus product bonds. So for this one, I'm going to break an HH bond and a ClCl bond, and we're going to form two HCl bonds. So mathematically, that's going to be 436 plus 242, the bonds of the reactants. I'm then going to subtract the bonds that are formed, the product bonds. I have two HCl's, and each HCl is 431. So it's like the 678 bonds broken minus 862, the bonds formed. You're going to get an overall minus 184 kilojoule value. This is an exothermic reaction. All right, you're going to get energy out upon making hydrogen chloride. So again, to do these kind of problems, you almost always need the Lewis structures, and then it's bonds broken minus bonds formed, or reactant bonds minus product bonds. Either way is fine.